Hi everybody. I'm coming to you here tonight. We had our first lab this week today, and after that lab, it seemed that many were still confused. So I wanted to make a quick video talking about what we're trying to do, giving it a better understanding, a better overview, and try to clarify a few points. So first of all, there's the clock, which I have up here on my screen, and you can see I've got a fast clock here that ticks. It has a 1, 2, 3, 4, 5, 6, 7, 8 periods. So from positive to positive, it has 8 of these periods here. And then I've got my divided clock, or my slow clock here, that is half of this clock. So the question here then that I keep getting is why 25 million in our case, or why half? So I think this diagram will help to visualize it better. Essentially, let's suppose for a minute that at the end of these 8 period cycles here, these 8 periods, we have counted 1 second. So we have the fast clock here is 8 hertz clock. It really doesn't matter because you can scale this up to any frequency you want. 8 is just an easy number to see on screen. So we have, let's say we have an 8 hertz clock here, and what we need then is a 1 hertz clock. We want to get from 8 hertz to 1 hertz. So that's what I have down here is a 1 hertz clock. I go from positive to negative, back to positive at the final period, or the final rising edge here of this 8 hertz clock. So right here is 1 second, and so then right here is 1 second. And you can see very clearly from this diagram, if I go 1, 2, 3, 4, 4 periods here, that is my up time. I need to be up for 4 of my periods because I have an 8 hertz clock, and then I need to be down for 4 of my periods, and then I need to come back up on that 4th period, on that next period. So this same concept scales to any size. So the question came up in lab today about 25 million being the correct number, and I started second guessing myself, so I had to pull it up here on the timing diagram to see it. But yeah, essentially we want to be up for half the time and down for half the time, and that will give us our 1 hertz clock. So we want to be up and then down. So 25 million is the number to go by. Okay, so I hope that this diagram helps you see that a little bit better. Again, this can scale, but the idea is the same. If we know that within however many cycles we have 1 second, then we want to be up for half of those cycles and down for half of those cycles, and so we can have a full 1 hertz clock. Excellent. All right, so then that kind of takes care of the clock question. So now the second question I think a lot of people were puzzled by is how do all of these pieces go together? And so I wanted to try and show you that without giving away all of the answers. So I've kind of come up with this generic finite state machine and state here. It bears a very strong resemblance to what you'll be doing. I've just changed some of the variable names and used a little bit of pseudocode because I don't want to give you all of the answers. I don't want you just copy and pasting what I've done here. I want you to think about what we're doing, but this will help you kind of understand a good way to separate your logic and help to keep it sane. So in our finite state machine, as I said before, all this is doing is tracking what state we're going to from one state to the next. So we have here these inputs. I called it go to A, go to B, and go to C. And then we have our output, which is just the state that we're in. We have our states here, A, B, and C. And I'm just saying if not go to A, then state is equal to A. If not go to B, then state is equal to B. Otherwise, state is equal to C. Now, why not? Why the exclamation mark here? That is because we're listening on the negative edge, and we're listening on the negative edge because our buttons on the not the microcontroller, but the FPGA are normally high. Now, some people were getting some errors saying that you can't do comparisons and inside the neg edge always block, and that is true. I had to look that up because I'd never seen that error before. Basically, you can't do this. That's not allowed because it's thinking you're trying to do some comparison, but all I know is that it's high or low. So instead of doing that, we just use the logical operator here, the exclamation mark OT. And that will compile, that will work without problems. So that solves that problem for you. Okay. And then, so in here I have the next module, which is the state decoder, which determines essentially what do we do once we have the state. So in here, I'm getting the input state, which when I instantiate this would be provided to me from the FSM. So it would be the output of the FSM going into the input of the state decoder. And then I have some internal registers here. I have an underscore clock, which I'll explain in a minute. I have a reset, and I have a latch value. Okay, so we talked about latches in the previous lecture. Essentially, what I'm doing here is I'm passing in my clock as the input to my latch. I've got the trigger, the thing that I'm using to control my latch is just this latch reg here, and the Q value or the output is this underscore clock. So I'm able now to save the previous state of clock by pulling the latch low. That will set the output of Q to be the previous D, which is in this case the previous clock. So that way I'm pausing the clock. Okay, so down here I've got this state block here, and this is where this is a purely combinational block. It should always be a purely combinational block. Its job, and you will typically have one of these. I'll describe the overall framework I'm using for this in just a minute, but you'll have a combinational block that relies really only on state, potentially some other inputs if your state changes, like based on different inputs. But you've got your that's the difference between a mealy and a Moore state machine. You'll be covering those in more detail in a future lecture. But for now, we're going to say that we only care about the state. So we'll look at the state, and we're going to say, okay, is state equal to A, fms.a specifically, because we're referencing this FSM. Did I write FMS? That should be FSM. Okay. So I've got this. If I'm in A, then I'm going to pull my latch low, and I'm going to toggle reset to be high. Reset being this piece of data here. If I'm in B, I'm going to toggle reset to be low and latch to be high. That means that the latch is transparent, so the clock just moves from D to Q. So from clock to underscore clock without any changes. Otherwise, reset is low, latch is low, so now we've paused the clock. And I don't need this last line here. So yeah, just reset is low and latch is low. And that's how we're going to handle our state changes. Really, that's all we care about. Pausing the clock will pause everything else for us. So that takes care of that for us. And then finally, we have here in the positive edge of the underscore clock, we are, as well as the positive edge of reset. We're checking to see, first of all, if it's reset, then O, that's the output. of this module, O, we'll say is equal to 0. Otherwise, if O is less than the max output, then O will be equal to whatever the next O value should be. And then otherwise, if neither of those are true, then O is still equal to 0. So there might be a more succinct way to write that, but this approach is perfectly fine. So this should give you a better understanding of how all of this is kind of working, how we can separate our pieces into distinct logic so that we aren't overlapping with trying to set values in multiple always blocks. Essentially, if you try and do something like this, for example, if I were to try and set O equals to 1 in something like this, I would get an error because I'm already driving O in this always block. I cannot drive it in this block also. So what I'm trying to do is find a way to separate out my considerations such that I don't have to have everything in one giant always block, and I can break the code up a little bit. It makes it easier to reason about. So the way that we've done this, it's called and now I've forgotten what it's called. I had to actually go back and review this before I made this video. It is called 3-process methodology. There it is. Thank you. So the 3-process methodology for state machines. Essentially what it means is that in the 3-process methodology, which is certainly the one I recommend, and this is the methodology for synthesizing state machines. So this is specifically for Verilog. What it states is that I will have a process, so I'll have one process for state transitions, which I'm handling in my FSM. That's all this is doing, is my state transitions. I will have one process, and when I say process, I'm referring to those always blocks, not necessarily modules. You could have multiple modules or a single module, but what I'm referring to is that I have essentially one always block that controls each of these concepts. So I have one process for state data changes. So that's this guy. It determines what state am I in and what does the data need to be depending on what state I'm in. And then I have one process for typically this is for sequential code. I just put for sequential code. A lot of times, depending on how your state machine is defined, the sequential code, well, for one process for reset. That's really probably the best way to put it is one process for reset. And reset, so I'll have one for state transitions, one for data changes, and one to handle reset. So I have it here. I've got, this is my reset block. It's also my counting block because it's convenient to have them in both since the reset needs to reset the count. So I'm looking at the underscore clock here, and I'm looking also at reset. I'm saying if reset, then set the clock to 0. Otherwise, go to the next next output, and if we are beyond the max output, then go back to 0. So we loop around now. That's what this one is doing. So this is the loop back. And you'll notice that if you convert this back into variable names and remove some of the pseudocode, you'll notice that this starts to look an awful lot like the state diagram that we built before, and that's intentional. So we have things like, the reset value that was part of our state that we decided we needed. I didn't do the whole thing, so you could put in some start or some stop as values as well, and build it. The point being that it's really up to you how you want to design it. I just highly recommend that you separate out these concerns so that you're not dealing with a situation where you need to set an output in some cases but not in others, and then you have an always block and you don't know what to do. Instead, separate these out so that you can specify sane outputs for every case. And the best way to do that is the 3-process methodology for state machines. I'm sure that there's probably a detailed description if I just go to Google and take a look at 3-process methodology FSM. Right here. For example, 1 versus 2 versus 3 style. These are the different styles that there are. So you can take a look at, here we go, here's another one from Stack Overflow. So these are really good details about how to, basically how to synthesize a state machine. They go into a lot more detail than I'm able to go to really in this video. I would highly recommend probably reading through, I think this Stack Overflow question right here is probably a good one to read through. I like the 3-process methodology. It makes the most sense to me. It's the easiest to reason about. This code is written in VHDL instead of Verilog, but the concept remains the same. You'll just have to do some translations. So at any rate, I hope that helps clear up some things. This week we're just going over questions and kind of helping you implement things. There's nothing new to go over, so please come prepared with more questions. I also will have help hours, office hours on Thursday and Friday. You can find those on Canvas. In fact, let me just do this as well while I'm here. I've had a few people ask me where you can find that information. So if you come over to 3700, courses, that's what I'm looking for, 3700, and you come down to lab resources. Then it says there are several videos, documents and other examples can be found under documents and examples. There's a Discord server, there's a Piazza page, and Lab TA office hours are Friday 2 p.m. to 3 p.m. and Thursdays from 6:30 p.m. to 7:30 p.m. in the Junior Hardware Lab. Remote options also are available by logging into the TA queue. So it actually is right there under lab resources. So if you're ever unsure, you can just go there and find it. I think that covers everything that I was hoping to cover. Let me know, again, guys, if you have other questions, if you need assistance with something I haven't covered. But I hope that this video kind of helps to give you a better idea of how to separate these things out in a way so that the logic is readable and maintainable.